Good afternoon and welcome to this doctoral thesis defense. I would especially like to welcome the doctoral candidate, Karsten Arnbjerg-Nielsen, and the two official opponents, Professor Markus Disse from the Department of Civil, Geo and Environmental Engineering at Technisches Universität München, Professor Haley Fowler from the School of Civil Engineering and Geosciences at Newcastle University. Also, a welcome to Peter Bauer-Gotwein from the Department of Environmental Engineering at the Technical University of Denmark. He is the chairman of the assessment committee. My name is Rasmus Larsen. I'm the university provost, and I'll be the chairman of today's proceedings. The doctoral thesis that we are considering today is entitled Panta Rhei, Non-stationarity in Planning, Designing and Operating Urban Drainage Systems. It was handed into the university in June 2019, and based on the assessment committee's positive assessment, the doctoral thesis was accepted for defense by the Academic Council on November 29th last year. The defense that we are having today. Now, the proceedings of the defense will be as follows. So after my small introduction, the doctoral candidate will present his thesis in a lecture of approximately 30 minutes. After that, I'll give the word to the official opponents who will discuss the thesis with the candidate. After that, there is the possibility of questions to the thesis ex auditorio. I have not been notified of any questions in beforehand. Now, if anyone wants to ask a question, they should register with me in the small break that we will have immediately after the lecture and before the official opponents start their discussion. I should inform everybody that the defense proceedings are being recorded, both for documentation and for the benefit of those who cannot be here today. After the lecture and the discussions and questions ex auditorio, the formal part of the thesis defense ends, and DTU will host a small reception in the lobby outside the auditorium, and you are all invited to join. Now, on the occasion of a thesis defense for the highest academic degree offered by the university, the Dr. Technicus degree, it is in 2020 impossible for me not to mention that this year we will be celebrating the 200-year anniversary of the discovery of electromagnetism by Professor Hans Christian Ørsted. Ørsted was undoubtedly the greatest Danish scientist of his time, and moreover, it was on his initiative that this university was founded in 1829. We will be celebrating this anniversary. DTU will lead a national dissemination initiative with many partners this year. We'll be celebrating the curious scientist and the impact of science through engineering and industrial ingenuity on our society. It is our plan that more than a third of the Danish population should meet Hans Christian Ørsted in one of the events that we organize this year. Now, Hans Christian Ørsted himself defended his doctoral thesis on September 5th, 1799 at the University of Copenhagen. That thesis was on Kantian nature philosophy. It was written in Latin, as was his later publication on the discovery of electromagnetism. Now, 2 weeks ago, we had another thesis defense in this room. That candidate claimed a proficiency in Latin. He was, however, surprised that the first question by the first opponent was actually posed in Latin. Now, I'm quite excited by the fact that the thesis that we have on consideration today begins in Greek. Panta Rhei, the summing up of the philosophy of Heraclitus of Ephesus. Will we continue in Greek when I give the word to Karsten Arnbjerg-Nielsen in a little while? Or should we prepare for a discussion of nature philosophy? Time will tell. Now I would like to invite Karsten Arnbjerg-Nielsen to the podium to present his work in the thesis Panta Rhei, Non-stationarity in planning, designing, and operating urban drainage systems. Please take the podium, Karsten.
Thank you, Rasmus. And I can assure you that I did not choose Panta Rhei because actually I thought it was Latin, but apparently now it seems to be Greek. So that tells something about hydrology. So I come out of the field of hydrology where we work with water, and in the International Hydrological Society, we have selected this decade of research to be the Panta Rhei decade. However, we have to change the homepage of the society because there it says it's Latin, and I never questioned that. So somebody must find out about that. Well, anyway. Moving on here, so I promised to stay within half an hour. We have 5 points that we would like to discuss. So an introduction, something about climate change impacts on extreme precipitation, and also coming back to say, okay, so those are the changes. What is actually the current climate? How is that like? And then some important other changes, and finally some conclusions. With that, moving on to the introduction, we have to start locally. In a field where everybody understands each other. So this is a small community, so 0.3 square kilometers, about 200 houses. That house is very dear to me. That's where my family lives. About somewhere between 500 and 900 students have been doing calculations on the hydrology of that house over the past 10 years because we're using it in the daily teaching. Today we're going to show a little bit differently. And first of all, I would like to introduce our local housing union association. It looks a bit odd to me. So why does it look like this? I mean, why not covering the middle, or why not down here? Part of the reason is that some of the areas actually developed quite a bit before. So down here we have a much older area that was developed before we started having housing unions. But this one in the middle, why do we have something? When you go into the area, you simply cannot see, and I had no idea when I bought the house that there was actually a difference in these housing unions. So it was first when we got the call for the annual meeting that I found out, okay, so actually there's a hole in the middle, and there are houses there, but they are not part of the union. In order to explore why, we have to organize a small badminton fight on flood risk. So I've chosen 6 people that are in the local badminton field. Some of them are living in the wrong areas, but we have Karsten Arnbjerg-Nielsen, who is sitting somewhere, I can't see him, over there. He was my boss for some years. Per is not known to this community, but his wife, Else Vad, is probably quite known. She was Jens Jørgen's boss for many years. And then we have Lars, Peter, and Klaus, who are nice people, but they don't know anything about water, which is, of course, a drawback. So the black guys are the flood risk guys, and the red guys are the unfortunate ones, we could say. Here we have a very weird thing. That's actually a stormwater detention pond, and the very first lesson you can get on flood risk management is when you see a stormwater detention pond in the middle of an area of houses and there's no river next to it, you have an issue. Never buy anything downstream of that. Some of them apparently did, so let's see where he comes from. You see this is the area that is contributing water. So whenever water is running or falling by fluvial storms onto this area, at one point this basin will be surcharging and it will be put directly on his property if there is enough water. Then we have 2 other guys in the middle of the catchment, and then of course you see the flood risk guys are right on the corners of the catchment. I should say this is not in the corner of the catchment, but we have a graveyard and some grass fields, so that's not really an issue. So the flood risk guys have placed themselves where they know there is no risk, and the other 3 guys may have done something that is not as smart as that. When we do the calculations, or so this is a professional software, we see that indeed there are 2 of these guys that do have a flood risk. It's not substantial. The catchment is too small to really be a very big flood risk, but there are changes. And when we come back to this figure here, then all of a sudden we realize why is it that we have chosen the area or the distinction between the housing union association and the other guys. Coming back to this, somebody developed this area to be flood risk or not being too wet. And then they decided, okay, what the heck, we'll make a bit more money of developing an area that really shouldn't be developed. They sold the area to some unknowing guys, the guys not knowing about flood risk or water in general. And then there's the guy down here who actually got a risk because the land was developed. So that is what Panta Rhei non-stationarity is about. That's about saying who has the knowledge at what time. So somebody will develop an area and they choose where to put their houses, and therefore they also choose whether people should be living in flood-prone areas, and also what are they putting a risk onto people that did not have a risk before there was actually some development. So it's about knowledge, it's about sharing that knowledge and making it available to the people that live in the area. I've been mentioning risk many times. We better define it in a proper way. So we are dealing with 3 components. One is the hazards, so cloudbursts, water and urban surfaces, etc. Another thing that's very important is the vulnerability. We need something that can be damaged, something that is dear to us, that one way or another will be damaged if something bad happens. And then the last one being the exposure, saying we need something that links what is vulnerable with what is dangerous. So the examples, we monetize that and say, so we look at a monetary cost over time. So that's the basic definition of risk, is that we will look at how much damage do we see per time unit. So just to give the examples, here's some hazard, dangerous or not, so you shouldn't continue driving when it looks like this. Vulnerability. This is the guy that had his house flooded. I'm sure you can see that the color here is not because the stones are different, that's because where the water was standing 2 hours before. The guy living next to this house was actually not trying to clean his house. He had a very beautiful garden, so he was out looking, trying to save his carps that were now escaping from his pond. So trying to come back on what is a monetary value on this guy not really caring about his house, but actually putting a higher value on his carps and on the beautiful garden that he had. So that is one of the issues that we have with flood risk, is actually trying to find out what is it that is dear to people and how do they lose that. Of course, exposure. Here we have a sea search where we see, so the hazard is for sure is there, so that's a sea search in Copenhagen in 2013. And here we see a wooden floor that definitely would not like that seawater to come in. And actually the windows are so tight that we are not seeing any exposure. So we need all 3 components. Basically, that's the framework that we have been exploring for the last decade or so. We're adding the risk here, and then we are seeing in an IPCC framework, so the Intergovernmental Panel of Climate Change, the hazards is governed by the climate. So what is the current climate? What is the current rate of cloudbursts? And then also what are the changes because we continue to emit greenhouse gases? That's coming from one side. And then there's the socio-economic processes. What do we do that either prevents or exacerbates these damages? What kind of governance structures should people know about the risk? Or do we want them not really to know about it because that will influence costs of housing, etc.? So those are the processes that come and dominate from the other side. I was so fortunate to be given the opportunity of going to GFZ in Potsdam and writing this thesis. And what I did first was to say, okay, what papers have I been writing over the past decade? So there were 66 papers, of which 62 fit into this diagram one way or another. 4 of them that were not related at all, 3 of them actually with Peter Bauer. And those are the ones that are over here as power water, not fitting into this diagram very nicely. Out of these, I chose 17 that are named or numbered in a completely different manner in the thesis. So those are the 7 papers that I thought would expose what I have been doing over the past decade together with other people. In the remainder of the talk, I'll focus on 3 of these areas. I'll focus very much on anthropogenic climate change, a little bit on natural variability, a little bit on socio-economic processes, and then an outro. The predicting of the climate change will do that by looking at how much will happen on scales of relevance for urban water management. So there are many, you can look at climate changes in so many ways. So what we've been doing is only how much will an urban infrastructure, urban water management be impacted. And we report it only as a climate factor, which is basically the future divided by the present, meaning that 10% increase of extreme precipitation will be a factor of 1.1. That should be fairly understandable. Doing that, we rely completely on people that are so different from us. They are physicists and they can model all the processes that goes on in the physics of how the world behaves, going from something that occurs on an hourly scale onto several millennia. They build models like that. It's a huge international collaboration. In Europe, the biggest organization is ECWMF. And their results is basically feeding into both what we look at every day as weather forecasts, but the same models, more or less, is also used for making predictions of what's going to happen on decadal and 100-year scales into the future. So we rely completely on the accuracy of these models, and we are really pushing them to the limit because we're both looking at small scales in time and space, and also something that happens rarely. So we're really pushing those models. They come basically, or overall, we tend to look at them of 3 model sorts. One of them is the model of everything, so the global circulation models. Those are the ones that you can actually see where you can resolve a hurricane directly. You can see that in the numerical model. Then you have the RCMs, the regional circulation models, typically on a mesoscale level, where you can see fronts moving over the area. And then you have the last ones being microscale, where actually you can perhaps see that we have reversed it. So the others are focused on the horizontal movement of the weather and the rainfall primarily. Whereas in the microscale, we're actually looking at how the water moves up and down into the air. So we call them convection permitting, because they allow the weather more or less to move up and down rather than just being passing over the catchment. It's completely needed in order for us to look at urban scales to go into the microscale and actually looking at how the water is moving up and down, because that's what's primarily happening in thunderstorms. However, what we typically have is the regional climate models, which do not have that capability, where we use numerical algorithms that compensate for the fact that they can actually not really resolve this up and down movement of the water. We have been able to look at the RCM scale and see what is actually the uncertainty. The first one would be the one that we typically apply. So in statistics, it's always best to use identically and independently distributed observations. So we take 15 model runs. Then we have an outcome, they say a climate factor between 1.05 and 1.15. So that will be the change over the 100 years. The only thing that's wrong with that is to assume that physicists are not only introvert, but they also refuse to talk to each other. They refuse to compare their results to anybody else and in any way interact. So, of course, they go to conferences, they talk, and nobody wants to be the one. If these guys, if there are 15 results out there, nobody wants to be the one who predicted it was 1.25, right? So something's wrong with my model, so I need to look at the others, what they are doing. So they, of course, they collaborate, and therefore, the information that we have is actually smaller than what is indicated by this black line of the bell curve of a normal distribution. If we account for this fact that physicists tend to collaborate, we get much more uncertain results, and also actually an increase in the climate factor. If we then also account for the fact that these models do not have this vertical movement, but only what focuses on the horizontal movement, so that they are able to compensate for the fact that there's things that they cannot commit. Then there's actually also a physical model structure error in their results, and that results in a bias in the actual results. And then we see again even more uncertainty and also a higher impact. So that's a result where we can use the RCM. So we know even there we can quantify pretty well what is the actual uncertainty of the climate changes on extreme precipitation. Going into an urban scale, we need to go to even higher return periods. So this was something that happens 5 times per year. Now we're going the other way to something that happens once every 5 years. And then we're looking at a temporal scale, not of daily input, but something that goes on down to 1 hour or perhaps even 5-10 minutes. This is actually where the majority of our sewer systems are designed, and the rest of them here in the detention area. So when looking at that, it's pretty clear that our RCM scale here only covers down to pretty much daily values, and it's difficult to go down to where we actually need them. So we need to compensate for this, and we would really like to get some local area models. Unfortunately, there was a seminar this morning, and somebody said, how can you get a disk and a computer that's big enough both to make these computations and also store them? And that is a huge issue, and we haven't really solved that yet, although we see some progress coming from certain universities. But this is what we get out of an RCM. So we can get the numbers, of course, it's a computational model. If we wanted to spit out results every hour, then it'll do that. But we can see here the differences between what the observations are and what the model spits out here on the daily scale is pretty low. But when we go out here on the hourly scale, this is the climate change signal, and we need to project it up here. So it's not easy to find out, so what is actually the impact of climate change over the very high durations? So that's what we've been spending a lot of time on, trying to bridge this gap of saying how can we extract information for the regional climate models that will give us the high resolution outcome in a way that makes sense. We have studied 3 methods. Common for them are that the uncertainty description is very difficult, so we cannot, like we did for the RCMs, get an overall idea about the uncertainty. But I've indicated one of the results here is that is trying to guess, so where in the world can we find a climate that resembles what we have in Denmark now? Where can we now find some measurements that has a climate that resembles what we will see in Denmark in the future? So in this figure here, it looks like we should go somewhere to France. Okay, that's not too bad. We'll do that and search for some rain data. And there are 2 other methods. So the important thing is that we must know that just like we saw on the other slides, when we go from the RCMs, these results have really an underestimation of the uncertainty. So we must look and take that as an absolute minimum requirement. This is the result, and this figure represents about 15 man-years of research. I see several PhD students in here, or people that were PhD students who contributed to this. First on the daily values, and this was the result I showed before with the bell curves. So the gray being the unreasonable estimates and the black one being the reasonable one. Then when we move this way in the figure, it becomes more and more rare results. So things that will happen more and more rarely. And we see overall modest uncertainties, but also modest changes, so something like 20%. That is if we take the pledges to the Paris Agreement, so something that is equivalent to something like 3-degree warming over the next 100 years, then we will see this 20% increase. So that is our best guess. These guys up here is then if we see more impacts. That was the daily values. If we go to the sub-daily values, then we no longer can apply this method, and we see some moderately increased numbers, but also if we do not follow the Paris Agreement and if people do not comply with the pledges that they made, we also see much larger impacts in the future of climate change impact. So it's not it does matter whether we actually emit more greenhouse gases or not. So if we continue as we've done over the past decades, then we will really be in trouble, because the rainfall is really going to change in a very, very crude manner. Okay, so the current climate, I have reduced down to one slide only. That was really a key issue that we were discussing all along the way when we tried to fix the future climate. That is saying, okay, so we predict these 20, 30, 40% change over time, over 100 years. We've seen something like 40, 50, 60% over the past 35 years. So either our models are wrong or there's something we're missing. So we made this graph. It's actually from Ida's PhD defense. That we can discuss the theory about it. It's not so nice, but this is the series that we have observed in Copenhagen. So 35 years of observations, and we see a change in climate extremes going from 1 to almost 1.9. So a 90% increase in Copenhagen, a little bit less in other regions of Denmark. But what we found out when we actually went back and took all the measurements of rainfall data that we have in Denmark, we saw a change so that, okay, we actually also did start right when we observed a historical low in the extreme precipitation. And as far as we could see, and we're going to find out in the coming years because we're making a new assessment, whether actually I'm pretty confident that we have seen a decline over the past 5 years. So we know for sure, okay, so our climate models is not as bad as we thought they were at one point. Still, we have the discussion and we have no idea about what is the truth. Is our climate factor something that already has kicked in here, or is it something that we need to add on top of that? So we defined and we are confident that our current climate is this level, but when we're making a prediction, so the 20 to 40% that we have recommended practice, is that with or without this 10 to 20% increase that we see over time? We don't know, and that's simply an uncertainty we have to deal with, or the future or the people after I've retired will have to deal with. I should say the prediction of ability of such a model is of course very poor, but still it gives an idea about how it would look like if this model was true. So the last scientific topic is socio-economic processes. We could also say, so we call it, so that's when the city also changes. So everything has been constant up till now, so the only thing that changed was the rainfall. We have heard about, and we started the introduction by talking about houses that change, or housing areas that are changing. The basic problem is this. We assume that climate change is something we can predict 100 years into the future, and then we build some projects that will take 1 or 10 years, between 1 and 10 years to build. And then everything will be constant over this entire 100 years. We actually even included in our laws, all our infrastructure in the in urban areas, so the pipes, by definition, they last 75 years. What we're forgetting is the fact that economists tell us that, well, actually you can never project anything more than 30 years into the future, because you may have a pipe, but nobody knows if you need it, and in that case, what you're going to use it for. So never trust anybody that tells you that you have something that lasts more than 30 years. And also, a pretty nasty thing here is the technical disruption. Right now, we're in the middle of a huge digitization process. Where will that take us? And we've seen many of such technological changes where we completely change paradigms. And we have to be honest and say, okay, we built some sewer pipes 150 years ago, but their purpose has actually changed 3 times over these 150 years. So perhaps it's even true for sewer systems that they are also disrupted every now and then. When we look at the areas connected to the central sewer system, then we made this analysis of Aarhus, one of the largest cities of Denmark. And you can see here the development of connected paved areas between 1930 and 2010. Now, we saw before that there was this change of flood risk in my little neighborhood of 0.3 square kilometers. Here we're talking about an area of something like 1,000 square kilometers. And you can imagine all of this water that comes down to some pipes that are lying here that were designed and built in the 1930s and have not been updated since. That's a lot of water that these guys need to cope with all of a sudden. Perhaps that's more than 20 to 40% over time. So that's a thing we need to look into also. It comes back to framing of urban drainage. We typically here train drainage engineers. They like to work with pipes or wastewater treatment. And if we do that, then our design criteria is extreme precipitation or sea level rise or something like that. But there's also a wider framing. That's the city layout. How do we actually plan our city? So where's the central station? Where's the airport? Where are the hospitals? Where do we have open land? There we talk about demography, land use. That's where risk assessments comes into play as well. The functions, that's really why we live in the cities, right? We don't live there because our house is there. Actually, we prefer to live somewhere else. We live there because of the functions. There are nice cafes, places to go to concerts, places to live or to stay, whatever. And that is personal preferences and willingness to change, individuality versus societal needs. The last one being the global drivers of equity, water, health, etc. So what we've been trying to do over the past decade is really to look at, we see the global drivers here as some scenarios that we cannot influence. So on the city scale or even regional scale or national scale, those are given. But we can define strategies that actually impact how we should counteract the impacts of these scenarios. And we can look at it either from the water infrastructure point of view, or we can try to be aggressive and say we need to also talk to the city layout and the city functions. So that's the fight. Will we be allowed to be part of defining not only the infrastructure, but also the urban layout? There are three ways of doing that. So essentially what we wish to do is looking at this one here. This is an urban area in a small part of Melbourne. This is one way of predicting the future. In Melbourne, you never can afford to buy a house. So what you buy is that you buy a house, tear it down and build 2 new houses on the same parcel. And you do that, and you can see all the blue houses here is a random number that generates. So where will they sell houses and where will they then build 2 new houses where there was 1 house? Alternatively, you can try to look at something that mitigates urban heat island impacts and creates more space for managing of water. And then you will build townhouses. You will be able to host the same amount of people in the area, but the urban layout will be different. So that's a way of looking at it. There are 3 ways of doing it. We have, or Roland I should say, have been doing it, looking at how does the preferences for development in Odense develop depending on whether we have residential blocks, row houses, industrial development, or single-family houses. And we can look at it and try to see how can we actually change these preferences by installing, for instance, the light rail of Odense. How will that change the city layout over time? We try that in the catchment of Melbourne, or the small part of it. This is the scenarios is either we know that Melbourne is going to grow. We also know that they're probably going to see a climate change impact on rainfall. If we don't see any climate change, then that is the green lines. Then we will in any case see a moderate increase in the flood risk. But if we see a high increase in the rainfall intensity, then we will also see a rather extreme increase in the flood risk over time. And here we're only looking 40 to 50 years into the future, not 100 years. If we install rainwater harvesting tanks, which is the Melbourne equivalent of a soakaway, meaning that there they would definitely not just throw the water into the subsurface, but they would use it for drinking water because they are short of water. Then that would not change the risk so much, but the city layout, as I showed before, really changes the things. Being aggressive in flood zoning, so saying here you're not allowed to build because here it is, or will be too risky to build. and we will even buy a house as it becomes too risky to live there. And you can also say we're upgrading the pipe infrastructure. You can look at it as the annual averages, as we've done in these lines that I've pointed at so far, or we can make contrasts of box plots saying, okay, here we see, okay, so it may not be a very big difference in the mean values, but we actually see that the most risky ones are really reduced a lot. And of course, the pipe infrastructure also is very, very efficient in minimizing the overall costs. So that's the kind of thing where we're trying to see how can we explore the efficiency of the strategies by making such contrasts and trying to use that as a communication tool of saying what is worthwhile to implement. So we're going close to 30 minutes. Conclusions, don't worry, there's lots to do yet, I think. One of the things that I've been focusing on is this risk framework. I've been trying, I've not been modest at all, but to say, so where have we made some substantial progress over the past decade? I can say that confidently because we're not alone. There are many people working on this field. I would say probably where we're needing to make impact now really is on the governance structures. There are many countries that are still struggling with if the information about flood risks should still be available, and if so, what should we do about it? But if we go to another level of saying, how do we actually frame the flood risk? What is it that we need? Then it becomes down to a matter of linking people and knowledge, and also finding out, so what is the right way? Perhaps it's not just the pluvial flood risk that is important. Perhaps it's how do we make good cities? That change will be a completely different paradigm in how we're looking at flood risk over time. There, I would say we have some huge issues still on flood risk management. We need to be able to find and communicate the flood risk to people. Also, I haven't seen anywhere in the world where they actually define very precisely what is actually an acceptable flood risk. So we talk about it being low or high, but nobody has ever said this is unacceptable or this is acceptable. And if they have said it acceptable, then it's typically because they're not living in the area themselves. Also, we need to have some implementation. We need to learn more from where people are implementing, how they're implementing, and how can we proceed from there, given the knowledge that they take up. Another thing is resource optimization, choosing the pathways, how can we improve over time. So I have here some sustainable development goals, so the UN goals for looking at how should we make the world a better place, both for nature and for people. And also the planetary boundaries, how to ensure that we can actually continue to live on this beautiful planet. We made a paper that was published just last Friday, so therefore I'm putting it up here. I think it's pretty fun, and also pretty much the entire section is part of the author list. It's trying to say where can we go? So urban water management, can we meet the sustainable development goals on water within preserving the planet? And I can tell you, you don't have to read the paper, the answer is no. In the sense that we're saying, okay, so basically we are spending about 20% of the allowable emissions of greenhouse gases on managing water in a place like Denmark. Because we have relatively clean groundwater, we spend much less energy than the average European or American population. So in principle, if for us to be sustainable, we can use economics as an indicator. So we should use about 1/6 of the energy or the CO2 emissions that we are using now in order to be sustainable from a CO2 emission perspective. That's pretty much what we should do on anything. So water management is not better or worse than many other targets. So whether we fly to Bangkok or we go on vacation or whatever, but we still have a huge challenge ahead. And going green is not enough. We simply need to go somewhere where we haven't been before. Finally, I think I'll pass the 30 minutes. There's been a lot of projects, a lot of people who has helped there. My family, customers, clients, colleagues, 44 master students. I can say number 1, 2, 33, and 44 is both here, all 4 here. So really great to see. I can also say that the majority of this work is really not done by me. It's done by the people that are listed there, especially. So they have been employed either as PhD students or postdocs, and many of them are still ongoing here at DTU, which is a great help for us. So with that, thank you. That was what I could squeeze into half an hour.
Thank you, Karsten. And we will now, as announced, have a small break until 2:45, where we will all reconvene for the discussion part of the defense. So see you in 5 minutes. Just getting ready to start again. Invited Professor Haley Fowler from Newcastle University to the podium to begin the discussion of the thesis with the doctoral candidate. So, Professor Fowler, please go ahead.
Right. Okay. Thank you. Okay. I'm delighted to be here, and thank you for your presentation, which I think really comprehensively covered what is a really thorough and detailed thesis. And you're covering 17 papers in that half an hour, so I think you did a really good job. I was wondering how you were going to do it actually, but yeah, thank you for that. I suppose, as you'd expect, I'm going to base my questions mainly around what you showed as points 2 and 3 on your diagram at the beginning of your talk, which is really concentrating on the definition of the hazard and how that hazard might change with climate change, which is really my area of expertise. But I'd also like to ask you a few questions about risk management more in general, and about flood risk management specifically, I suppose. I thought to start with, it might be nice to have a more general question. This is probably quite a difficult question, actually. But I mean, you've done a lot of work in this area now. And I wonder, how do we actually find the right balance between this uncertainty in defining the hazard and actually the need for model complexity for urban drainage? And it's a big question.
Yeah, and I think to me that's actually a comfort of having the second part of the thesis, in the sense of saying when we predict climate change over 100 years, then it's typically because we need 100 years to really see the change and kind of get rid of all these current climate fluctuations. But that also means that we're looking on such a long time horizon that no matter what we do, we are wrong. And also that the impacts that we're modeling are relatively low compared to what we see in urban development and technological disruption and things like that. So, but we had a large discussion. I think one of the papers, the one that was led by Bruno Merz, we had quite large discussions in the group of authors, where some of them said we should use the very best and most advanced methods that we can possibly employ. And I was more saying, no, we need some methods that are as far away from each other as we can get, so that we can try to get a grasp of the overall uncertainty, because we know that we cannot perceive. I mean, you know that when you base all your knowledge on a model, then a model is also a smoother, that the reality is more complex than the model, and we are overly confident in the model outcomes. So I think the only thing we can say is that we're pushing the climate model so far, and it's only a model, and therefore the complexity is bigger in reality. So therefore the uncertainty and the real unknowns in this is bigger than the models can predict. So we know that, okay, so we said, okay, 20 to 40% in 100 years time, but we know that the uncertainty is much larger. I think what we can honestly say is that, okay, we can honestly say that probably there's less than 3% chance that we will not see an increase in extreme precipitation. And then we need to take that into account in our planning. We're saying we know it'll get worse. We don't really know how much, but we need a number, and therefore, for the planning purposes, we use these 20 to 40%.
Yeah. Yeah.
I don't know if that is a...
Yeah, no, I think, so it's, I mean, are you saying therefore that it's not, well, maybe it's more important to understand that the hazard is increasing and be more qualitative about it than perhaps come up with very precise quantitative estimates. And therefore, I don't know, do we need to look at, well, I mean, okay, so perhaps the model complexity comes in with hydrodynamic models or whatever it is. Do you think there's still room for methods like the rational method then? Because I mean, you talk about that in your thesis right at the beginning, and you know, that's a lot of, it's a very simple method, but a lot of urban drainage design still hangs off these simple methods.
Yeah, perhaps the rational method is simply a method where we, by means of simple free parameters that you base on the physics of the area, you can design pretty much 50% of your sewer system. Mm-hmm. And the point is that we spent, I think that was in the 80s and 90s, but we spent decades of research trying to find out methods that were much better than the rational methods. And what we found out was not so much a systematic being better, but what we found out was that before the 80s and 90s, we had designed systems where we had a lot of, we call them now inherent or unconscious safety into the system. So we choose a larger pipe than is really there. So we choose a lower concentration time, all of these things. And basically what that meant was that we built systems that were more resilient than they are today. So now I think in general, and we just finished the course last Friday where we teach the student to optimize and find the best solution that as cheaply as possible can get exactly what we need to get out of it. What you also have to recognize is that when you do that, then you're also building a system that more easily becomes very vulnerable, because when that design value is exceeded, then you see much bigger changes than you would otherwise have done, or damages than you would otherwise have done. Mm-hmm. Mm-hmm. So we have a risk, and I think our strategy with, or our approach with strategies and scenarios is a call to say to the engineering community, don't over-engineer, but build systems that are robust across many things. It means it'll never be perfect. No matter what, you will find perhaps solutions that are equally good or a little bit better, somewhat cheaper. But overall, this is a good approach.
Mm-hmm. Okay. Yeah, no, I agree with you actually in terms of, I suppose, the need to bring in different methods to produce robust solutions for management. I suppose another question then, a sort of more general question before I ask you about some of the rainfall aspects. I mean, do you think the design storm is dead? Should we only be using continuous modelling now? And how do we do that?
Let me put it this way. When I made my PhD back in the 90s, I was convinced that the design storm would be dead by now.
Yeah.
It still goes on. We have people actively trying to kill it, sitting in the audience. We have to recognize also that when you are going into a new built area, you cannot sit there and do thousands of simulations. You need something that's quick and rapid, and your 1 year of research will still only make the pipe size go from here to here, or perhaps here to here. So the extra cost of choosing this pipe rather than this pipe is 4%. It's not worth it. So therefore, our design storms will in many cases be sufficient, because it's a simple way of designing things that don't need more complexity. Mm-hmm. Mm-hmm. We also have tunnels in Denmark being designed right now where, I mean, you can have two vans driving in them in parallel, because they are so big, and they are only to be used for rainwater once every 10 years. There, of course, a design storm concept needs to be reevaluated and reassessed, and there we should do more, probably.
Okay. Yeah, I mean, I've got some questions about that. Okay. So, I mean, I guess this is a question that sort of leads on from my first question. So, is defining, I mean, maybe you've said this already, but it seems to me that, well, no, is defining the hazard well the most important part of urban flood risk management, would you say?
I think where we have the largest uncertainties, both in assessing current values and also in projecting the future, is really the vulnerability. We had a huge storm in 2011 in Copenhagen. It was the biggest insurance event in Northern Europe that year. There were a lot of historical artifacts that were lost because they were stored in a basement that nobody thought could be flooded. It was flooded. A hospital was about this amount of water level from being the trauma center of the national hospital was that close to being flooded. So what is the cost of such an event? We have the work by, I think it was Umanu Lal, that showed that the flooding of Bangkok back in 2012 led to a global lack of hard disks. So there's a limit to how much we can actually predict is the costing. So we can use PMPs, or we can use some other methods of saying this is the worst that can happen in the hazards. Some people don't believe us. Nobody believed that the event in Copenhagen was possible, although we were people saying that will happen at some point. But nobody could project that there will be a global shortage of hard disks in anywhere because of a flood event in Bangkok. And I think really the vulnerabilities where we have difficulties projecting and foreseeing what can go wrong.
Yeah.
So I really like what you do in England on the hazards, and I think it's really fun to dig into that part. But also I have to be honest and say it's the vulnerability, which is also a social science aspect, that is really the largest uncertainty in actually setting up, and probably what is preventing us from setting actually what is an acceptable flood risk.
Yeah. No, I mean, that was one of my final questions, actually. Maybe I'll have it now. So, I mean, yeah, I mean, I agree with you. So, I think most current flood risk management is about reducing the exposure to the hazard. Yeah. And all of our hydrodynamic models that you use, that my group uses, that are used to design and plan for these type of events, they're really about reducing exposure, mainly through structural changes. But I think, how can we really elicit reductions in vulnerability, and how can we actually test that in a modelling sense? Or, I mean, it's a really difficult question.
Yeah, I guess it comes back to also the definition of resilience that we have so difficult. I mean, everybody's talking about resilience. It's a great term because everybody puts into the word what they would like it to be, right? And one of the things that is really difficult in that context is saying part of the solution and part of the concept of resilience is decentralization. But our models are pretty bad at predicting what is going on in a decentralized setting. It's much easier to prevent or to predict dikes and dike breaches than it is to prevent 10 different structures that together should form the same protection. Our models have shortages, our conceptual understanding have shortages in trying to define what is actually resilient in a way that makes sense. I don't know if that answers part of your question, but I think that's where we need to go and to build models that understand this complexity and embrace it, rather than just saying, okay, we know exactly what a dike will do and therefore we put that there.
I mean, I suppose it's also embracing the different connections across space and time scales as well, which I don't think we do very effectively at the moment. We're, very much based on the very local scales in terms of flood risk management, and maybe we need to be thinking a bit more broadly about that systems connectivity as well. I mean, I thought it was really interesting the comments that you made at the end about energy efficiency, actually, and the need for energy reductions, and how that feeds into kind of a systems approach to building cities of the future in terms of reducing carbon emissions, but also providing, better flood risk management as well as other services as well. Yeah, okay. Right, I'll move on to some more specific questions about, I think it was chapter, I can't remember now, about basically where you're looking, chapter 4, I think it was, of your, chapter 4, where you're talking about modelling hazards in the thesis.
I'll try to put it up here on the screen.
Oh, okay, yeah.
So there's an issue in the sense that the page numbers that she's referring to are not the same page numbers that you are having, because you wanted it to be, what is that called? Reduced in size, so therefore we had to use more pages. So approximately what page are you on?
Oh, okay. No, I mean...
you weren't on a page, sorry.
That's fine. I will be in a minute, don't worry.
Okay.
Okay, so I think what you identified as a key deficiency in this chapter is really the representation of spatial rainfall, actually, and that variability over space, which obviously impacts a lot on the actual flooding in an individual location. And I mean, you make some points basically about, and I think these hold across different models, that there's a much higher correlation spatially in certainly regional climate models than in observations, and I think that holds true for these new convection permitting models as well. There's a problem with using our standard statistical techniques, I think, extreme value analysis, in terms of this sort of IID assumption. I mean, I think how with this issue of spatial dependence and the pattern being key for flooding, and the fact that we at the moment use point level return periods for design, I wonder whether there's for me a bit of an incompatibility between the fact that we use point level estimates. Maybe you could first comment upon that, and do we need to be moving to more spatial aspects, and then how do we actually characterize that, I suppose, both in observations and in models, and do we need new sort of statistical techniques to do this? They're big questions.
Thank you. I think we need to break it into two. So it's one of the things that, I mean, one of the things that I wrap up in the text is saying we need to bridge and align rural hydrology with urban hydrology.
Yeah.
And one of the issues that are there is the fact that in catchment hydrology, you always use spatially gridded data. So you have soil moisture, water content in the air, precipitation data, spatially distributed over the catchment, and you have 20 years of measurement or something like that. But it's also on daily values, on daily measurements typically. In urban scales, we go down to 10 minutes or even 5 minutes, and there the correlation structure is completely different. And we know from the re-analysis data that it's really difficult to fill in the gaps of a higher resolution than daily data and this 25 by 25 kilometer grid that you typically use in catchment hydrology. I see a huge potential and in especially the radar data that we're seeing, we're getting improved measurement techniques, so dual polar and all the other things that I will not go into because there are people who know more about than I do here. But we can measure data in a better way than we could, and we get them in a higher resolution. And therefore my hope is that we at least get the observations that will enable us to do what they have done in catchment hydrology for many years. But then we come back to how can we utilize that in an urban drainage situation, because we are coming from the infrastructure part where we want to design things. And we will never get a global coverage of 10-minute data and 20 years of observations of everything. So how do we move this data from, let's say, Denmark to Sweden or Jutland to Zealand? Is really a key issue, because if you move it 50 kilometers and make this 20-year simulations, then you'll get one result. If you move it 60 kilometers, you will still cover your catchment, but you will get a different result, because I would say, okay, this huge rainfall now actually just was outside of the catchment rather than inside. So our way of transferring this spatially gridded data onto a new location where there is no measurements because there is no city yet, or the city is completely different, and then making these simulations and finding a traditional one-dimensional design as an engineer is a huge task, and I'm not sure we covered that. As you may see in the thesis, I tried to make some initial things in the thesis, trying to say, okay, what is it that we need for certain kind of design things? And then I said, okay, let me try to, and then in the end I said, okay, this is not a task for me anymore. You need probably more statistics and more process understanding than I do in order to really solve this issue. I hope, and I think it's definitely a requirement, that we get the data that I'm seeing coming now. I don't think it will be enough. We also need to really think about how to use that more data for making changes, because engineering is about not making the optimal for now, but recognizing what changes come in and take them into account in what we do. So I don't know if that was a very elegant and long way of not answering your question, but
no, I mean, I think you you did answer the question. I mean, I think we're doing some quite interesting work on this at the moment in terms of, I mean, just this spatial dependence in climate models means that you can't use typical extreme value methods, and you need to account for this spatial dependence somehow in your estimates of return levels. But you're right, I mean, you need to get really strong statisticians involved. And so, I mean, another aspect you touched on then, I think, which I had a question about as well, you're talking, I mean, one of the problems with both information from climate models, particularly these very high resolution models, and from observations of very short duration, you know, very high temporal resolution observations, is that they're quite short. And that's the case all over the world. You know, the longest time series we have go back about 100 years or so for 10-minute data, but certainly in most regions they go back 20 years if you're lucky. And so it's, and you know, you make quite a nice case in this chapter for sort of reconciling those short records with longer term time series. But I mean, and I think you have a paper right at the end of the thesis where you try to bring in that non-stationarity into the design. But I mean, how do you think we can do more to actually account for this non-stationarity in planning? And I mean, you touched on this in your presentation as well. You know, this natural variability is always there, and it's always going to be there, actually. And you're quite right that there is that great uncertainty about where that 30 or 40% increase comes from. You know, does it come just from that natural variability? Does only 10% of it come from warming, or does all of it come from warming? And it really depends on your baseline and your future. And it's trying to sort of characterise that and come up with some kind of robust estimates so that you don't over-design. I wonder whether you've got any thoughts on how we might do that.
I think there are two ways of approaching that. Actually, no, I'll go another way. The thing about optimization in a design situation is that you tend to only focus on what is the optimal value. If we build something that is too small, we save money on the investment, capital cost, but we get higher flood risk, and vice versa. And all the studies that we've seen is that for urban infrastructure and in particular stormwater systems, it's actually a very flat optimum. So I would say, rather than spending a lot of time on seeing what is the true optimum, I would think it would be time to start asking questions like, how can we actually ensure, or who should take care of the fact that if we build something larger, then everybody's protecting to save a few, or vice versa. So what is the common problem and what is the individual problem? I would argue for the fact that we should go for high protection standards, mainly because we are a rich society, and rich societies take care of the ones who are in need. And we will all proliferate by choosing a high design standard. I should also say that this is completely against any utility company with a rational mind, and if the engineers understand it and accept it, then for sure the economists in their investment, whatever unit that's called, will say that I'm completely off. Because of course for the utility companies it's about getting relatively cheap investments and low capital costs, so that they can say, okay, we saved money and here you have your money back. But it is at the expense of the common good. I mean, I started by showing these two people that had flood risk in my local community. It's an acceptable flood risk to me because it's something that happens every, let's say, for one of them at least it's something like something that happens with 5% chance of a year maximum, probably even less. And there he will be completely compensated by an insurance company. But if we chose a 1% standard, it would be a relatively low extra investment. Of course, we would need to be sure one way or another that the insurance didn't still claim the premium for covering his costs. But we would all be benefiting from the fact that we would have a more secure society, one risk less or one hazard less to take care of. But that's more a political answer than a scientific one, I realize that.
I mean, you made a comment on this at the end of your presentation, actually, about how do you actually define an acceptable flood risk? And I mean, I think you're quite right at the moment that that tends to be defined by, or at least because we rely on insurance, and that insurance pays out at the moment, and you can insure properties against flood risk. I imagine that could potentially change in the future. At some point, you know, maybe that acceptable flood risk changes, or I think it's really interesting, actually, how do you actually define an acceptable flood risk? And I mean, the finance world are really thinking about this at the moment in terms of investment decisions they make with climate change, and at the moment, those investments are protected by insurance, but actually at some point in the future they expect that extreme events will become more frequent. They are now, I would argue, and they perhaps become uninsurable, and at that point maybe that is when your flood risk is unacceptable. I don't know whether you've got any comments on that area as well. How do you define that acceptable level?
Acceptability is one thing, but there's a paper that Bruno Mertz and Roland Löw and I have been trying to frame for the last 2 years on actually saying why is it that it's a step towards getting a definition of an acceptable flood risk, and that's the mere concept of getting people to learn from other catchments, right? Copenhagen was taken completely by surprise in 2011. They had never anticipated that such a thing could happen. Except that Greve was hit in 2002, Aalborg in 2004, Odense in 2006, Aarhus in 2007. Why should Copenhagen not be met? I mean, of course they should be hit at one point. But they thought that their sewer system was better than the others, and therefore they didn't need to do anything. So a structured way of learning and saying, why is it that everybody needs to learn by themselves? Why is it that, I mean, we did a study together with Heidi Freilich and I think 30 other people in trying to look at what happens in the catchment that has personally, or I should say the catchment itself has experienced the flood. There we see a tremendous increase in both reduction of exposure and vulnerability. They have learned. And the learning continues for decades. And for sure Copenhagen will have learned a lesson. They will be much more resilient and much more flood safe for decades to come. But why is it that Stockholm or Munich or Newcastle, or why is it that these cities, why is it that they should all then individually experience, so this is what happens to my city when it goes bad? I think that's really a key issue, rather than saying everybody should have the same standard. It should be everybody should be forced to have a common learning. And I think it's really, I mean, we have people sitting here knowing about chemistry. So we have the REACH directive that puts very strict limits on, they don't think it's strict, but relatively strict limits on, so these are the amount of concentrations that you can have of these compounds in this soil, blah, blah, blah. It took forever for the European Commission to issue a floods directive. And one of the things they discussed was what is an acceptable flood risk, and they simply, the only way they could push it through was to give up the idea about having a common acceptable flood risk standard in Europe. So they talk about rare and non-rare, and you kind of get an idea that a 1% chance per year, so a 100-year storm, is the difference between a rare and a non-rare.
Mm-hmm.
But they don't say that this is something that you should take into account in your planning. So on the political level, it's so difficult to enforce this, but I think learning would be the first and really a needed step to go there.
Oh yeah, and, I mean, I agree actually. I think there needs to be much more focus on reducing vulnerability through whatever it is, experiential learning. So I guess an individual doesn't have to experience a flood event, but that learning can somehow be transferred into vulnerability reductions at local scales with individuals before the flood event happens there, and then therefore reducing the exposure as well. Actually, I suppose in that photo you showed of, you know, the doors not opening during the flood event. Yeah, I think that's really important as well, and it's something that's not really been thought about enough yet. Okay, I'm just trying to think. I had a couple of technical questions actually about this chapter as well, since you've got it up there. Yeah, so figure 4.4. Yeah, I mean, I was really fascinated by this figure, and probably everybody's going, why? But so I'm really interested in why the 1 hour event maps so well onto the mean annual precipitation, simply because it's completely different to what we see in the UK. I don't know whether this is just the methodology that was used to produce it, but certainly in the UK, we almost have the opposite happening. So in the south, where you have quite low mean annual precipitation, you actually get quite high peak 1 hour rainfall intensities, and actually you would expect the 24-hour to map much better onto mean annual precipitation than the 1 hour. Yeah. So I don't know whether you have an explanation for that.
I think the best explanation is that we don't have any mountains. So you have a lot of orographic effects in the UK that we don't see here. So the reason why these two subtiles are identical is because that's the only covariate that there is. So the model simply looks at the mean 2-year event for 1 hour, and then the only covariate there is actually the mean annual precipitation. So we don't see any impact from, or the impact that we see from orographic variation, north, south, whatever, is all taken into account by just using the mean annual precipitation as a covariate. So of course in meters above sea level, or I think it's one of the ones that uses the covariate in the UK, and also distance from coast. They are not present. They are in Denmark
not
encountered.
We
studied several times, tried to find better covariates. We didn't succeed.
Okay, that's quite interesting. So why does the 24-hour not map onto that?
The 24-hour doesn't map onto that because we found another extreme statistic, which is what we call this climate grid Denmark mean daily rainfall extremes, which is, as far as I recall, something equivalent of the 0.2-year return period of a gridded data set, so a data set that we have for the entire Denmark.
Okay.
And we correlated the approximately 100 gauges that we have with that covariate for the daily rainfall, and there we saw a very significant correlation. So there we have, so for the 24 hours we both have the mean annual precipitation and the climate grid Denmark as covariates. One for the rate of the occurrences, which is the mean annual precipitation, and the other is the size of the observations, which is the climate grid Denmark.
Okay. Yeah, I guess I'm still a little bit surprised that yeah, well, maybe there's not as much, or there isn't as much difference between different regions of Denmark in terms of mean annual precipitation as there is in the UK. But yeah, I'm still a little bit surprised that you get such a close mapping. So I wanted to ask something about...
I mean, there is, of course, an issue, I should say, also in the 1 hour model being the one that really explains the least of our things. So I actually think, I can't recall, but it's something like 5% of the overall variation that this model actually explains. So there's also it's not a good model, it's just the best model that we could find.
At the moment, okay. Yeah. So I wanted to ask something then about, I suppose, climate change and how do we design climate uplifts or climate allowances. And obviously you've done a lot of work on using different regional climate models, and also using different methods as well that you've mentioned. You certainly mentioned analogues in your presentation, but you also, in the thesis, mentioned the use of stochastic rainfall models, which I've obviously done a lot of work on in the past, but not for quite a while now, actually. So, I mean, figure 4.7, you also showed in your presentation, or a kind of version of it. I mean, how do we start to reconcile that difference between what you see in observations and what you see in regional climate models?
Well, I think one of the things actually that I didn't mention is that the grey lines in that figure is actually the raw model output statistics from this model. So that is an average over 625 square kilometers or something like this.
Okay.
So accounting for what we in hydrology typically call an areal reduction factor, then actually the solid grey line on the daily scale is very close to the black line.
Oh, good. Okay.
So that pretty much
So that's accounted for it. Yeah.
But that also, because it's on a log scale, it makes the differences to the convection area of the figure even more dramatic, right? Because the areal reduction factor would be lower, but the distance up to, or the differences between the scales have become more large.
And one thing I didn't, I suppose, see in the thesis is any work on convection permitting models, although you obviously mentioned them. And I obviously do a lot of work on these things. And are you starting to do work in that area now as well, in terms of using these to develop climate allowances?
Yes, we have recently started that. I should also say that's where my knowledge stops. We have a good collaboration with the National Met Office, just like you do, and it's simply not within. There was not a financial climate in Denmark that enabled us or enabled the Met Office to go into convection permitting models at the time. Perhaps also I don't know. It has changed now, so we are producing convection permitting models for Denmark. Actually, we just got funding to do some simulations on the ECWF, where we'll try to do some simulations on a 700-meter grid.
Oh wow!
That we will go into, because I mean, we know that there is a difference between what we call convection permitting models and models that actually permit convection, and we know that we need to go down and really should work on a scale of, let's say, half a kilometer. 700 meters was a compromise. What I see also, the work by Emma, we see that the convection permitting models are very good at looking at the high resolution variation. So the convection permitting models make rainfall that look like rainfall.
Yeah.
Perhaps to the audience, there was a slide that I would really have loved to show during the presentation that I couldn't show because of time constraints. So just to give you an idea, so this is the kind of rain, this is the area of sealant, and then these rainfall intensities that you see there, that's rainfall passing over sealant in a regional climate model. So that is the kind of information that we extract and try to make real convective rainfall on. This is a rain weather generator that's actually produced by one of Hayes' colleagues at Newcastle. So this is so far away from real rainfall that it's obvious that we need to do something completely different in order to get real rainfall. Convection permitting models, when we do a similar analysis or simply say visual approval of the convection permitting models, they look like rainfall, right? It's like seeing a video from a radar. But some of the statistics that we employ also indicated that, well, what they are may be that they're very good at taking this high resolution and take something that looks like rainfall. But when you aggregate to a little bit higher scale, let's say hours and a few kilometers, then it's too variable. So it's not consistent enough. So this thing about the RCMs being consistent on the daily scale and 1,000 square kilometers, and the local area models or convection permitting models being consistent on the very high resolution scale, but the bridge going from both having the real good convection storms and the good frontal storms in one model seems not to have been solved yet. That's my preliminary hypothesis, at least. We haven't worked as much with it as you have. So.
Okay. Yeah, I mean, well, yeah, certainly we haven't. I mean, it seems that the projections of change from the convection permitting models are very similar in terms of mean climate to coarser resolution models, and certainly for winter extremes they're very similar as well. Just the summer extremes tend to be quite different in terms of the projections. Okay, I mean, I suppose you've just mentioned statistics. I mean, one of my questions was what properties of these models do you think, or I guess what properties of the observations do you think the models need to reproduce to be useful in urban design? And how do we actually assess their performance?
Good question. I'm not sure, really. I think we have to realize also at some point that climate change models are also in some ways made to project a future that none of the people that are making them really wants to see come true.
Oh yeah.
It's also a political statement of seeing, do we really want to see a 6-degree warmer world? No, we don't. And so this is what's going to happen. So please take some action that prevents us from going there. So therefore, I fully understand the idea that the models are primarily built in order to project temperature because it's a simple metric that can be understood and can be used to produce policies. It's also very clear, at least from my biased opinion, that it's not temperature that's the most important variable. That would be extreme properties of rainfall for flash floods, also for fluvial floods, and in particular, of course, for droughts. Right, over the past 10 years, we've seen 5 megacities being days from running out of water.
Yep.
You have had a drought in England. Who would ever think that would be possible? All of these things, right? I mean, Johannesburg, Los Angeles, Sydney, Madras, Chennai is the name now. These cities running dry is horrible, but we're not there where the model can actually predict that to a sufficient level yet. I would say.
I mean, certainly we can't forecast those type of events. Yeah. I mean, I agree, and you're right that models probably don't represent extremes well enough. I mean, I thought that some of the work that you show in your thesis in terms of using lots of different methods to come up with more robust estimates is really interesting. And I wonder, I mean, I have this argument with people at the Met Office all the time now, actually. And one of the things that's happened as part of the UK climate projections that have just been released is there's no longer a weather generator, for example. They decided they don't need one anymore. It's not necessary to have a weather generator because we now have convection permitting model outputs. Yeah. So, I mean, I wonder whether you have any thoughts on whether you think these things will replace methods like, for example, weather generators or analogues. Is there still a role for statistical downscaling methods in these design methods moving forwards?
What you're coming into is saying, so what climate services should we be providing? And I was not aware that was a part of your new release. I mean, for sure, entire Europe and probably or all that were concerned with climate projections and making that into climate services that could be used by people looked towards the UK, and when I think it was UK SIP 9 was released. Tremendous progress in actually delivering data that could be utilized for enterprises looking at protecting their own premises or city governors or whatever. I think we have to realize that in some ways people are getting more and more educated, but also in some ways it's getting more and more complex to understand and translate the information into something that can be used.
Absolutely.
And perhaps on a more simple level, I have every year, I don't know, 5-10 people coming that asks me of, should I buy that house because it's that flood prone? And because I have the knowledge, it takes me less than 5 or 10 minutes to say, okay, yes or no. But for people that don't know where they should go, it's all public, it's all available. It's just not made readily accessible to people. And I would say that demanding that people can themselves make a weather generator and apply it and interpret that knowledge in a useful way is demanding too much of people. I think we need to do something. I think you had the flood risk handbook that gave national averages.
Yeah.
And I think you need things like that in order to make it, to avoid mistakes in designing. So that we need to say, okay, for things that cover these 95% of all design situations, use this. And then if you want to go beyond that, then you go there. We have the same situation in Denmark where we're discussing whether we should, there's been some very interesting work on spatial, a mixture of spatial and point measurements using that for design. And it's been applied and it's been shown for some of the tunnels in Copenhagen that there is a huge potential for saving money. And we've had quite some arguments in the professional societies of whether and to what extent we should make that available to everybody. Because if we just release it as it is, then my belief is that then we'll see a lot of under-designed sewer systems in Denmark because it's so easy to misunderstand what goes on in those methods. And I think that's where we need to go and say, so we need to give information that we think people can manage and utilize in a proper way. And then we also need to tell them that there are more advanced methods that in some cases will be able to save you money. But I would say building a weather generator, yes, it's easy to install rain sim, it's not easy to get robust estimates. To comment a little bit on the Newcastle.
No, I know. I mean, I think the problem with all of these methods, and whether it's statistical downscaling or dynamical downscaling.
Sorry?
The problem with all methods, whether it's statistical downscaling methods or whether you use dynamical downscaling, so you use regional climate models or convection permitting models, is they all have their own idiosyncrasies, they all have their own biases, they all have their own problems. You know, the weather generator produces extremes reasonably well up to a certain return level and then not above that really. It doesn't really produce persistent events like droughts, so there's issues with that. You know, at the same time you have regional climate models that really don't reproduce, or global climate models for that matter, don't reproduce these very persistent anticyclonic conditions, but also can't reproduce those very large extremes either, potentially. you know, and then you've got analogues that obviously have their own issues, because you're never going to have the exact same climate in Copenhagen that you have, say, in, I don't know, where it would be, somewhere in middle of France or something. You know, I'm guessing. But, you know, you're never going to have the same climate as Paris here, almost certainly. There'll be some differences, but you're trying to find an analogue that fits well. And I think that what is nice with some of the work that you've done is that you've actually brought some of these different methods together, and I think therefore you can, if they then start to agree, and we did a similar work in the UK where we used a sort of temperature related method, an analogue method and a convection permitting model to give us estimates of change for the future, and when they start to converge you have much more confidence in your estimates, I think, when they're from kind of independent sources, perhaps.
Yeah, or perhaps I'd be even more happy if they didn't converge, in the sense that it would give us an estimate of the true uncertainty that is there. Convergence is nice because you have a nice number that you can communicate, but I think it's also fair to say, okay, 20 to 40% is what we communicate in Denmark, but I think we also remember to tell them every time, yes, it could also be 100% and it could be 0%. Take that into account when you design, so don't trust the 40% too much. I was very skeptical. I mean, the first paper we did on this back in 2012, my biggest concern was that the numbers were too homogeneous, right? I mean, you take 3 results and you get the exact same numbers. It was really a surprise to me. I had thought and hoped that there would be a bigger difference. And that was actually a key, that was the key reason why I was very happy about Marie Saunier's work that I presented here on getting the actual knowledge of the RCMs, because showing how uncertain that information is, and then intuitively just going from saying, oh, okay, an average over 600 square kilometers, so 1/3 of Copenhagen area-wise and daily, and taking that into something that is 5% of Copenhagen and on, let's say, half an hour, and a thing that happens every 5 years, every 10 years. It's such a huge uncertainty. It must be very uncertain, right? So it's trying to buy a car, and you go to the dealer and you say, and you promise them that you'll never drive more than 20 kilometers per hour, and then you buy it, and then you go on the highway with 200 kilometers per hour and say, okay, I know exactly how it behaves because I drove it with 20 kilometers an hour. That's what we're doing with the climate models now. So I'm not sure we should expect a consistent signal. I would be more confident with us seeing a wide variety of something that would be more closer to the actual state of knowledge that we have. But I understand the
Yeah, I mean, I would like to hope that as we get closer to understanding the processes behind these events and how they might change, that we start to converge. You will still have uncertainty, and that will come from mostly from emissions. So, you know, what future we choose to follow. As you say, we always tend to follow these very high-end futures in climate modelling because it produces the most change, and that's good in terms of making an impact. And of course, that is actually the future we're following at the moment, if not slightly higher actually than those high-end scenarios. So it's quite realistic in terms of if we don't do anything. So my hope would be, as we understand more and we get better models, you actually start to converge. But I can see that for a robust solution, you need to look at all of those uncertainties. So this is probably a good point actually to ask you about. You make a comment, I think it's chapter 3. Chapter 3, yeah. Right at the beginning, about it's a shortcoming that the IPCC terminology does not provide a tangible indicator to be used for hydraulic design, and a more quantitative framework is needed. And I think that's really interesting actually, because I think that's something that's coming up again and again at the moment. And I don't know whether you came across a paper by Rowan Sutton, which was published last year. And if not, you should probably read it, but it's really interesting. And he talks about this need for the IPCC to really change and to move away from climate science, and I mean, I think it's called something like climate science needs to take risk assessment much more seriously. Yeah. He talks about the fact that in Working Group 1, the summary for policymakers of the 5th assessment report, risk is only mentioned once in that entire... So risk, the word, is only mentioned once in that entire summary. And risk assessment is never mentioned. Yeah. And in fact, at the moment, the IPCC reports really concentrate on that likely range, rather than looking at what he thinks we need to know, which is what events are plausible, how likely are they, and what could their impacts be. And I've certainly been talking to the flood risk manager at the Environment Agency recently as well, and they're very interested in this idea of plausible extreme events, and particularly for short durations, and how do we how do we use these, and particularly plausible worst case events. And I think that that's a really, really interesting in terms of, moving towards that kind of paradigm and terminology, and that a shift perhaps in the way the IPCC reports on these things could actually be quite advantageous for flood risk management as well as other management, actually. I wonder if you'd like to comment on that.
I think there. First of all, I agree fully with the point of view saying that we need that. We have to recognize also that risk is a term that everybody uses, and it has both a scientific meaning, and it has even 10 scientific meanings within 10 different disciplines, and then there's an everyday meaning. So that's one thing. I'm not sure the IPCC could do that in the sense that the IPCC is still a governmentally driven organization, and whether the governments are willing to accept the fact that they are going in this direction of making poor decisions, I don't know. I think the IPCC made a huge work. I think there was up to assessment report 4, where they unified terms about how certain we are about things. And that is more or less a unification of the hazards, saying so more likely than not, very likely, unequivocal, and all these terms. And I fully agree it would be great if we could get a similar term for what is actually acceptable risk. On the political stand, I would say we have a very interesting situation in Denmark that is very different from the UK. I have here a mapping of, I can't recall, I think it's Scotland somewhere, where we have the flood risk here as the blue lines, and then we have a mapping of where do we have people that are multiply deprived, so people that are poor and or disabled one way or another. And we see in the UK that there's a very clear correlation between people that have a flood hazard risk, a flood risk, and many other risks. We have a very interesting situation in Denmark in the sense that if we did the similar mapping in Denmark, it would be the multiply the people that are really resourceful, because the flood risk level in Denmark has been so low for decades that people have forgotten about the risks. So therefore it's very rich people that are very resourceful, that are actually living in the most flood-prone areas. Okay. And therefore we're actually seeing some very interesting psychological phenomena in the sense of people moving there, because we see that we have very resourceful that has a lot of their funding invested in where they live or make their living, and they are the ones who are really going to lose big time on the flood risks. And we see some dynamics there that we don't see in, okay, so it's the poor that are being flooded, that's good because they're cheaper, because they don't have as much value in their house. We have the other dynamics here. And perhaps that'll be an eye-opener, and it'll be really interesting to see how that evolves over time in Denmark. And that's one of the very interesting things where we'll see probably a difference in Denmark from many other countries.
Yeah, I mean, I suppose that gives them the capacity to actually reduce their vulnerability, though, because they can spend money on the problem. Whereas, yeah, I mean, if you're already, very deprived, you just don't have the money. You might not even have flood insurance, actually.
Yeah.
So I think that's part of the issue as well. And then every time you get flooded, the government has to bail you out. Yeah. But it's also, I mean, partly to do with the fact that the way the flood spending, defence spending works in the UK, where actually it's the economic value that you basically decide how to spend the money on flood defences through the economic value of the area that's going to be flooded. So obviously that's going to predominantly protect rich areas, and therefore, basically there's a lot of areas that are poorer that don't get defended adequately, I think. Right, just have a look. So I've got a couple of final questions for you. So I think one of the first ones is really thinking about the modelling that you're doing in terms of the hydrodynamic modelling. And my question is really, do we need to move to risk-oriented dynamic management? Do we need to actually take the dynamics into account more in flood risk planning, and particularly in flood forecasting, I suppose, that dynamic movement of things, the changing hazard, exposure and vulnerability as part of the modelling system, and how might we do this?
Are you talking now about the hydrodynamic model, so the way we move transport water in pipes, or other kinds of dynamics?
I'm, I suppose, talking about surface water dynamics, probably.
Sorry?
Surface water dynamics?
Yeah. I can say that what we have been doing has been so far, where we were when the thesis was submitted, was very much, we set a standard. So we proved that we can do 12,000 simulations of a 1D, 2D modeling system and make an accurate assessment of that. And we have done that, or at least my purpose of doing that was to say, we never have to do that again. We need to find simpler ways of doing it, right? I mean, it took an HPC environment, and I think it took us about 4 months of doing these calculations, and it's not been done before. I hope it'll never be done again. It's something that we needed in order to establish the baseline, and what we have been working on ever since is to identify statistical or mechanistic emulators that can mimic this dynamic, so we never have to make such advanced things again. Also because the real issue in that is that we cannot make realistic adaptation options. We cannot explore that in a sufficiently dynamic way, because installing and upgrading a sewer system with 10,000 pipes is extremely difficult in such a complex model. So we have made extremely simple strategies for that. So we simply we just tear out the sewer system and then we throw it in either now or 10 years later, and I don't know how many years they'd have to close Copenhagen if we just installed a new sewer system and said, okay, this day we close Copenhagen, then we open again when we have a new sewer system. It's not a viable approach, but that's what you have to do in such a complicated model setup. So we need to make something simpler to be able to explore strategies that are realistic. So that is something that we will work on.
And a final question, I guess, then is around data and digitization, I suppose, and this big data, the fact that we can now collect data about everything, and we do collect data about everything. And certainly in Newcastle, we've got something called the Urban Observatory, where we collect data on air pollution, on movement in pipes, whatever it is. Basically, we collect all of this data, CCTV images, everything. And I just wonder how that sort of move to data collection and almost you've got data on everything happening. How will that improve flood risk management? How can you see that feeding into the type of models you're developing?
There I see two scenarios, an optimistic and a pessimistic one. When we get more data, we also implicitly get more knowledge. However, we fear that we are going into what some at our section is calling data-rich, information-poor sampling strategies. And my concern is that we get so much data on things that happen on a day-to-day basis, that we forget about things that happen rarely, whether that is flood risk or failures, breakdowns of the system, dam breaches. There are so many things that can go wrong, but that is not in our data collection of 20 or 30 years. We have a huge debate. It took, when we designed the Great Belt Bridge in the 1980s, there was a huge study in Denmark that showed us that once every 150 years approximately, we have some really severe storms coming in from the Baltic Sea. And we had these huge discussions with the national authorities on whether that should be made public or taken into account in climate change adaptation or coastal management. Simply because that was not in the data. No, because the data collection started after we had that huge storm in 1872.
Yeah.
So data started. So when you look in the data records, you cannot see a sea surge in Copenhagen that's bigger than 1.6 meters. And the extreme value distribution that they're using, saying, okay, we can never have a sea surge in Copenhagen that's bigger than 1.9 meters above the regular sea level. But we have already had more than 4 meters in the, or more than 3.7 meters in Copenhagen. So we've seen it back in 1760. We also seen more than 2 meters back in 1872.
Yeah.
So what if we use digitization, if we use more data collection to improve the day-to-day value while preserving our knowledge about what can go wrong, then it'll be good, really good. If we focus so much on the nitty-gritty details of those and forget about what can happen, then it'll really be bad. So we're losing the memory of why we are doing flood risk management, right? So then we'll focus so much on the small storms that we never think about the big ones. We need the learning that enables digitization to take the knowledge from where it has happened to where it might also happen.
Yeah. Okay. No, I think that's a really nice answer, actually. And I think that's really important in terms of the use of historical information, actually, to inform flood risk management as well, which we don't use enough of, I agree with. But yet at the same time we can try and use these new data sources to try and inform the, I suppose to fine-tune models, to try and really improve that actual model predictions at the smaller scales. Yeah. Thank you. Yeah, it's been a pleasure talking to you. Yeah, okay.
Thank you, Professor Fowler. And now I'd like to invite Professor Disse from Technisches Universität München to the podium to continue the discussion.
It's on? Ah, yeah. Yes, thank you very much. Hello, Karsten. You're a poor guy, 2 hours already. But
I'm
I
more
think
concerned about the people here.
yes, that all the people has to listen. And I think perhaps we can do it in half an hour or 40 minutes or so. First of all, I was struggling a little bit with the title of your thesis, Panta Rhei, Non-stationarity in planning, designing and operating urban drainage systems. For me, it sounds like a good engineering approach. And I did not see so much in your presentation. What is your solution for planning, designing, and operating urban drainage system?
Thanks. I guess you're right. It's so much about presenting solutions as it is about let me start by an example.
Okay.
I was asked to review a document that was looking at the flood risk of Copenhagen, a certain part of Copenhagen that's very vulnerable, because that's where, if that is flooded, then the Copenhagen metro will be out of service for 2 years.
Mm-hmm.
So what we did was that we had a dike, and then on the back side of the dike there was a flat land, and then there was a small dike, and then there was a depression, and in the depression is where this very vulnerable metro service center lies. So the consultant who did the work set up a model saying, okay, we'll have the storm surge, it'll take 24 hours, then the water will flow in, and then you will fill up the bathtub here between the two dikes, and then it'll surcharge into the service area. And I was asked to say, okay, is the dike level here of I can't recall, 5.4 or something meters, is that the right level? And then you're saying, okay, so there's uncertainty in how long the storm is. We haven't actually recorded one of these storms with an accurate time recording. The uncertainty on the level of this 2,000-year storm is 0.5 meter. And so if there's 0.5 meter or 1 meter of water standing above this dike, ensuring that it will come into this bathtub, this astronomical difference, right?
Yes.
Then you're filling up the bathtub, and then you're putting the water into the service area. So they spent half a year probably, or they charged the metro company half a year of doing this work, right? Can you say that it's wrong? But you start off by saying, okay, this 0.5 meter here is really the dominating uncertainty. And whether you say it should be 4.7 or 5.4 meters, you cannot say either of these solutions are wrong. You cannot say that it's not a 2,000-year storm and that this is protected against a 2,000-year solution. So my point is more being of saying we need to stop doing these very detailed where we make assumptions as engineers until we have a problem that we can understand. And we need to embrace the uncertainties that are there and then look for solutions that make sense. So rather than saying, okay, my question is the size of this dike, then the very minimum you could do is to say, okay, what is the cost of constructing this dike versus the cost of not having a metro for 2 years, and then make the economic assessment and then saying, does it then make sense to make it this high, or should it be higher, or should it be lower? Rather than just saying, okay, 2,000-year storm is what is the right answer, and then you make simplifications until you understand the problem. So I think that's my overall message in this context. So it's not coming up with yet another approach for designing things in a way that we understand, but trying to embrace the uncertainties that are out there and that we need to take into account in order to make things that actually work in practice and not primarily work under the assumptions that we think are needed to understand the problem.
So okay, so in your title, urban drainage system is not the pipes, not the grey infrastructure, is more than that, yes. And okay, you're dealing with the deep uncertainty. I think you called it deep uncertainty, and so integrated solutions are necessary. And you told us this dike is also a constructive building, so you have to construct something. How do you think about these green solutions? Or you did not talk about sponge cities, for instance. Do you have a meaning for that? Is it more for minor cases, or can it really serve also for extremes?
When I started at DTU in 2008, we had a huge discussion on green versus grey. I was on the grey side in the sense that I said, okay, if you want the cheapest possible solution of ensuring the current design standards, then the grey solutions are out. And nobody listened to me continuing saying, but we need them anyway. Because they only heard the first thing, and the grey people were happy because they didn't need to change anything, and the green people were happy because they had somebody that they did not like. So that was very, very simple roles to play. But when you go into an area like Australia, their water management practices where every person spends 300 liters of water per day. Some of it is spent on preserving water in their gardens, and they still put water in the sewer pipes. It's a completely disastrous system, right? We need cities that are resilient. Part of being resilient is to ensure that the water is there and offers livability every day. So if you make only the infrastructure optimization, it'll be an answer of saying, yes, it's great. If you want to build a resilient city, it has to be green. As part of the solution. Then we're discussing, the Dutch are very proud about the Room for the River project. To me, that's such a heavily engineered project that it's hardly green at all. But we need to be in this struggle of saying we need hybrids, right? We are in the Anthropocene, so we need to build something. We are designing something, and therefore, by definition, it's whether we're using plants or concrete, it's still human engineered. But let's do something that enables us to be in a nice location.
Would this also affect your cost-benefit analysis? Because you have spoken about the cost of the dike and the benefits of the tube that is not flooded. Are there other benefits then in your cost-benefit calculation if you go more for green solutions?
For sure, there are recreational and aesthetic and health reasons why we should have the green solutions. The problem is that, I mean, you can monetize it. I mean, you're going to the non-market assessments, and we actually had a master student and currently have 2 PhD students trying to quantify these values. We are not there yet, and to me, it's not so much an issue of finding the value. It's more finding out who will pay for that value to become true, right? Because installing a green area in this part of the city will help the people that are there, but the municipality and the mayor is assessed also heavily on the fact that he will get taxpayers to the municipality. So somebody should compensate that mayor for retaining the green space rather than ensuring more taxpayers. So we know that there's a green value, we know that there's aesthetics. People pay fortunes for living close to nature, especially in a country like Denmark where we have so little. So of course there is a benefit. The problem is finding out who is actually going to say, I'm going to pay for that, so the common good, or who will actually insure it. I think that's a bigger issue than actually getting the cost. So, but we cannot go and say finding out that, so therefore we're trying to monetize the green values.
But also the effectiveness of green solutions can be much higher than grey solutions. Do you think so? Other question, how would you design this city of Lyngby in a perfect way against higher floods, not 20-year floods? 20-year floods are done by the drainage systems, but 100-year floods. How would you design it?
Rasmus, can you close your ears for a moment?
If you are the mayor and you have the right
we
party.
can start by DTU.
Okay, or DTU.
When DTU was designed in the 70s, we had a very innovative approach to managing our stormwater. So we actually ensured that almost all the water was managed by that kind of high technology at that time called infiltration trenches. So we had soakways, I think it was close to 200 kilometers. And we installed the manholes were installed of regular depth, and then they had to flood for a while, and then we would have rather high-lying pipes that were penetrable, which also meant that they were also infiltrating water while it was running. That system retained more than 80% of the water falling on the DTU campus within the DTU campus, so it was infiltrated. So only 20% emitted. Now we're building like hell out here, and we're taking all these 200 kilometers pretty much removed now.
You forgot the solution, or no, you cannot forget it because.
Well, you know how it is. So we're the environmental department. Here's the campus management section. Here's the management secretariat, and getting that to work is not always easy. Not in particular, perhaps not at the university. I thought we had a good system, and we demonstrated in practice that it worked. And that it was a good solution. It worked for 40 years. Of course, it's also, I mean, these systems are old now. The technology is outdated. They need heavy renovation. But it was a good system. And now, because of simple savings and because people don't know exactly where the pipes are, we're just building traditional systems, and we're putting much more polluted water into the local river. I would like to have seen us trying to retain as much as possible the water's balance of this campus still, and doing that all over Lyngby for that matter.
So I heard from Los Angeles a report that nowadays in LA every new building has to infiltrate all its surface water. That's a law, a new Water Act law in California, and I thought it's so old solutions, but perhaps it's a little bit forgotten because of growing cities. You spoke also about these growing, there's also a paper about that the two uncertainties are the climate change, how the precipitation will change, and how the cities will grow. Okay, all these cost-benefit analysis are based on these two uncertainties. But how a city can grow, that can be managed by us. The climate, perhaps it's too late and we don't know really. But how to build a city, that could be really, easily made. Also for the cellars, for instance, you know Wolfgang Krohn, for instance, he always says, my mother has a cellar with no assets in the cellar, and now we have all the electronics there, and the vulnerability is much higher. Why don't we go that old ideas which are, you don't need a calculator for that? What's the reason? Are we doing some fancy calculations, but the simple solutions are not on our screen? Or are they? What is the reason why we don't do this integrated flood risk management and reducing vulnerability by simple means?
I think the part of the answer is that it's not simple to retain the natural city or the natural environment. I mean, what is simple is to build something where, I mean, we've been building sewer systems for more than a century. We know exactly how they function, we know exactly how big they should be, and we know that it works. Sometimes when we install, I mean, going back to my first example with the badminton guys, if we try to install soakaways there, then the guy in the middle of the catchment, that house would be uninhabitable, right? So there would be, in our little district area there of 200 houses, there would all of a sudden be 10 houses that could no longer be inhabited because we were used to having the sewer pipes, so we lowered the groundwater level. Now all of a sudden we infiltrate so much water that actually the groundwater level comes up and that guy will lose his house.
But you can forbid a cellar, and then you increase the houses for 1 meter, like it is done in some parts of Germany and of Denmark as well, I think, these waft houses, and then this could be a simple law from the mayor that these new houses have to build 1 meter higher, on higher ground without a cellar, and vulnerability is nearly zero then. Yeah. So it's crazy a little bit.
It's an option. we still have a lot of old houses, and we need a gradual. We need to take care of all the houses that were built there at certain periods and were inhabitable by some people. And when we make these changes, how should we implement them in a way that are fair? I don't think there is an easy answer.
And I would like to come back to the word of resilience. You said, okay, there are so many definitions of resilience. How would you define resilience? And is it helpful for flood risk management, the buzzword resilience? How would you define it?
I cannot define it, but I think there are 3 different ways of looking at it. Here I'm looking at it. So we have the technical resilience, which is this graph. I'm pretty sure you're familiar with it, saying that resilience can be defined as how severely is a city impacted and for how long time does it take to recover. So that's a technical resilience measure, and that's a simple way of defining it. But it's not the only definition that's out there, and I'm not sure this is the right definition, because this is something that you typically apply on a machinery or something like that. In a city, you will never go back to the same, right? When you make adaptation or something, you'll move to something that is different. Right. So eventually you'll have a better city than you had before the event. So there, oh, I'm sorry, this is apparently in Danish. Another way of making resilience is to ensure that there are more people and the organizations are more complex, so that if one fails, then another kind of organization will step in, so that you engage more people in the process rather than saying, okay, so either utility company or the contingent investor people or the engineers or whatever will take care of the issue, then actually educating the population and saying we need for many people to be aware of this risk, so that we have several organizations that take it into account in their planning process. And then of course on the global level it's the donut economy, I think is the most common term for it, saying that we are constantly struggling with a trajectory. So every time we take a decision, we should go from something that we have some global planetary pressures on the resources that are pushing us and put some boundaries to what we can do. And then we have an internal boundary of saying we should all have better lives than we as good lives as we can. And every time we take a decision, we should try to go for a solution that brings us towards something that brings us in a better space where we use less resources while still providing better goods for the people that are living in the area.
Yeah. But perhaps coming back to the engineering resilience, the most simple one, and the first one, I think it's very important to consider the recovery time also for the cost-benefit analysis and also for decision making. I have an example, for instance, we had a big flood, what was a river flood in Germany, and the railway was totally disrupted and destroyed. And the Deutsche Bahn said, okay, I will build at the same place, the same railway road, because it's more resilient, because it's much more effort to plan a new route for the railway. It costs years and millions of money, so I took the same place. But in fact, I know perhaps in 20 years it will be washed away again. But it's better to be here. I can repair it in 2 years and not planning it in 10 years for a new railway system. Therefore, we should also consider this recovery phase, and does it make sense? Or to make the same mistake, so to say, again, it could be meaningful. Yeah.
I think you can respond to that in two ways. I think so. One is to say that I was in Sendai shortly after the tsunami. Touring that area is probably the worst thing I've ever tried in my professional life, because there they took the other decision of saying we need to find out where the railroad is going to be before we will start building anything in the city. So I mean, basically 70% of the city that I was going out to had been washed away, and people were living families were living in 40-foot containers, and 1 or 2 people were living in 20-foot containers. And I saw numbers on the suicide rates in these containers. So these people waiting for somebody to decide where the train route was going to be before they could start building the city were putting so much pressure on these people that they were simply giving up life. So there's a limit to how much we can delay that decision. I know also, I mean, some of the things that I saw at GFZ in Potsdam that was very interesting was that they were looking at it and saying, when you're assessing a risk like a railroad, that is not a voluntary risk that you're taking, and therefore you cannot apply cost-benefit analyses. And one of the arguments that I'm making in the thesis is that we look at cost-benefit analysis and say we should always have a positive outcome. We forget that is, in a risk management system, a cost-benefit analysis is something you do once you're accepted that this risk is acceptable. So what Patrick and some of the other guys were doing was that they were actually multiplying the expected annual damages by a factor of somewhere between 10 and 100 to account for the fact that, okay, people here are exposed to a risk of not being able to go to work because this railroad is gone. So their costs should not just be the lack of travel time, but it should be
it's a cascading effect.
And I think that's one way of doing it, or simply saying we cannot accept that railroads are failing more often than, let's say, 1 in 1,000 years or something like that.
So it's difficult to really put it into numbers, and all cost-benefit analysis and also resilience analysis are prone to human judgment, let's say, or manipulation, if you say another word. Perhaps one question to this precipitation forecast and the numerical weather models, which can perhaps solve convective rainfall. For urban floods, is it so necessary to have this tool? Because there's anyway nearly no forecast lead time. So you have to make robust systems that can sustain a flash flood, and you have no time to pack sandbags somewhere or so. So perhaps we need only a rough estimation. There could be a thunderstorm in the city of Copenhagen. Okay, please close your doors, close your windows, and so on. And that's all. Do we need such sophisticated high-resolution models? What do you think?
I can say that my decision on not applying for funding until we had conviction permitting models covering Denmark was actually by a paper by Haley, was one of the authors in Nature Climate Change in 2014, where they said, okay, so the climate change impact will be different for different spatial scales. So all the things that we were doing on point estimates, at least 20 to 40%, our hypothesis and our assumption is that we can account for the rest by means of aerial reduction factors and other traditional hydrological means. But what they showed, or at least I don't know how much we can perhaps talk about that later, but what they showed was that there was a spatial component also, so that climate change would be worse at the point scale, but it would be even worse on, should we say, convective scale, so somewhere between 5 or 8 kilometers, we would see higher impacts than just on the point scale. So that means that we were underestimating the 20 to 40%. As soon as you took it into a sewer system, those 20 to 40% should be 60%. And in order to, so we couldn't continue on normal RCM models when that assumption was there. We need that information in order to get better models. So it's a key assumption of either validating or falsifying the information that was there, both, of course, in the models that is now run on the European scale, but also many other places in the world, to see if this spatial component is actually there or whether there was an artifact in the first non-convective model, convection permitting model. So I would say they are needed simply because we need to understand whether our assumption of the spatial structure of rainfall will remain the same or change.
Yeah, but I think it's a fundamental difference for designing, what you say here, planning, designing, and operating a system. So for planning, designing, perhaps a rough estimate is okay, because you need a number for the designing something, and if it's a 100 year or the 200 year, who knows in the future? Nobody knows. But for the operating, you need a forecast. Is it possible in the near future that we can forecast flash floods with a lead time of, let's say, 3 hours or 6 hours or even 12 hours? Is it because the thunderstorms are really, you said spatial resolution must be very, very fine to protect the university or to protect the hospital, or what else?
Yeah, there you have a point. On the operation scale, there is a limit to how precisely you can predict.
Yeah.
I mean, one of the things that went bad in Copenhagen in 2011 was the fact that there were absolutely no warnings issued. So the head of contingency in Copenhagen was actually having a day off, sitting in this barbecue up in northern Zealand, because all the projections were saying, okay, this huge rainfall is going to be there, but it's going to fall in Malmö, so 40 kilometers away. That was another country, so there was absolutely no risk or no warnings issued. We still have that issue.
But how? What is it in the near future, in 10 years from now?
Perhaps I should ask projection on the scientific field that I know nothing about. That'll be a guess. I don't think we can do that. I mean, that way that is too chaotic a process of knowing where exactly these vertical movements will start. I don't think we will make substantial progress on that. But on the other hand, I think also that for many of the operating schemes, it's not so much whether it's a 100 or 1,000 or a 10,000 year storm. It's more, is it going to rain? Is it going to rain a lot, or is it going to be really a lot?
Yeah.
And mostly your control paradigms within the urban water management is really not about protecting towards the very extreme, but either choosing between, let's say, 4 domains and then issue the warnings relative to that. And there, I think we're already there, and I don't think we need more than we have in order to make that kind of assessment.
And therefore, so static flood risk maps would be sufficient, that you have before the static flood risk maps for some return levels, and then you say, okay, this part of the city is most vulnerable, they have to evacuate people, and here we have more time. So that not a real forecast, but choosing maps, choosing right maps if the event is coming. Yeah, I agree. I would also think so.
We've had discussions with the national contingency guys in Denmark saying that we would like to do a reenactment of the flood event that occurred in 1872, so that they meet, let's say, every 2 months, and then they have the knowledge one day more into the future, or perhaps just 6 hours into the future, and then saying, okay, now we know that this is going to be really bad, so what can we do? So what are the things that we're going to move around? How are we going to evacuate people, inform people, etc.? I think this is would be a vastly fun exercise to be part of, and it would be highly needed before. You have so many exercises of contingency measures that are people running around with pumps doing some regular, relatively low extreme events rather than these really severe storms that really blow things away.
Yeah. For me, I was also a little bit puzzled, but because it's Denmark, I think. Denmark is very flat, right? And we have no hills in Denmark. Okay. Therefore, for us, flash floods or urban flooding is also related to the surrounding catchment. So our biggest events was not just falling rainfall in the city. Okay, Münster perhaps is an exception, but normally we have water delivered from the catchment, including mud and drifting wood and so on. It's and you wrote in your dissertation, your doctoral thesis, that we are going more for hydrology now, urban hydrology. Yeah, so we have to use hydrological models more in the city, not the simple. How do you?
IDF curves.
Yes. No, simple things. So first question isn't it an issue also in Denmark, the catchment around the city, which is prone to flash floods? And secondly, which kind of hydrological model would you use? Would you use models which are used by the wastewater management departments mostly, with the Abflussbeiwertverfahren, sorry for the German, or more sophisticated model? What would you say?
We have huge issues making the boundary conditions between the different modeling paradigms, and we have so much issues in saying that this water comes from this model understanding into this model understanding of the urban and the rural scale. I think the solution will be, as we discussed with Haley, of saying that we need the higher resolution so we can actually take one model system, whether that should be Mach Chi or Mach 2D or something, that could be have a representation of rainfall and topsoil dynamics and rivers that are on the scale where the cities are represented in a sufficient accurate way. So it should be 10-minute data, 500-meter resolution, something like that, and then accept the fact that that's way too complicated for it to be needed in the rural scale, but making it run in the same modeling complex would be so much ideal in order to avoid misinterpretations.
But you have not such a huge problem here in Denmark with a delivery of water from the catchment. That is more real urban flooding, or what you had?
We tend to say no, but that's perhaps also because Aarhus and Copenhagen, the two big cities, doesn't. If you go to some of the other cities, we have a small city in northwestern Jutland called Holstebro. They for sure would disagree with this because they took a river and then they built a bridge on top of it, and they put a hotel on top of the bridge, and then they made the bridge slightly smaller or more narrow than they did before, and now they have, I think they had 5 floodings in 8 years. So they for sure experience a mixture of pluvial and fluvial soils. Also we see, especially in Copenhagen, a lot of dikes being built which will really exacerbate sea surges and pluvial storms. But it's right, we don't have many rivers in Denmark, and therefore what you see as the biggest problem in Germany is the combination of pluvial and fluvial.
Right.
That we don't see. But if you go to Hamburg, we their situation, their problem we really see in Denmark, several places also. And the problem in Copenhagen is that we only have a very few lakes, and they were not natural, and the only natural lake we had in Copenhagen has been dried out. So the water system in Copenhagen is not really natural. So that way it's difficult to compare.
And okay, if you imagine now that a village is also threatened by the catchment, so by fluvial, it's not really fluvial because the water can come from everywhere in such a situation. How would you manage this? Would you also go for grey or more for green solutions? Okay, it's case dependent, of course, but generally speaking, do you have trust in ecological farming for increasing the infiltration, or planting mixed forests instead of having big retention basins? Or do you have a guess, or do you?
I mean, you have the Dutch Room for the River project, which says that green is everywhere, but
the Dutch? Or?
The Dutch Room for the River.
Room for the rivers, yeah. Yeah, for the big rivers, yeah. There's no way.
In that way, when you look at the Dutch Room for the River project, it's also very much about building and constructing and building things that look green, but are really 100% engineered. So I think we will have to use a mixture of that. And also, like we've done with, somebody did in Prague, where you have these mobile barriers that you can put up and then have some immediate protection. And if that is not enough, then you have some outside of Prague agreements with landowners outside of Prague saying that your land will be flooded rather than flooding Prague next time. So I think we need that kind of system, right? And setting up compensation schemes so that you know immediately that, okay, we're going to set this up at a certain point, and we assess that every 50 years we're going to use your land for flooding because it's better than flooding the capital. I think we're going to see measures like that occurring.
And so by far more effective than to tell the farmers, please don't use your plow. Yeah,
but also, I mean,
I agree.
Part of this is also talking about compensation schemes, right? Because the farmers, right now the narrative is that, okay, it's better to flood the farmers than it is to flood the city. And that's just something the farmers have to live with. And of course they should be compensated, right? And so there's a negotiation there that we need to go into and be honest about saying, so yes, we need to build a dike around Copenhagen, so nature about Copenhagen is going to be destroyed. That also means that there are other areas in Denmark where we probably should preserve nature at the cost of retaining the people that are there. That's an example of where they want to do that in Odense. Should they pay for it themselves? No, of course that's a national problem, that we need nature as I don't even know the English terms for it, but natural areas in Denmark should be there, and it should not be up to just the national or the municipal authorities to ensure that they're there.
Would you say then that the government should care about all the flood issues? So in Bavaria we have now the shift giving more responsibility to the people, to the inhabitants. They should build their houses accordingly, flood-resistant houses and so on. But we can also think that perhaps the government gets a tax, a flood penny or something like this, and then the government can decide where to build flood retention polders, where to build, not to build houses, where to forbid cellars, and so on and so on. That's a good idea, as a centralized solution from the government and supported by experts like you.
You always need a mix of local and central solutions in setting up such things.
Yeah, the governmental solution could also be decentralized solutions, but that there's only one voice, so to say.
for sure, some of the things. I mean, we set up a national trust fund, saying that everybody who owns a house should pay for houses that are flooded from sea surges. But there, the insurance scheme is that you need to build exactly the same house at exactly the same location, just like you talked about that already. So of course we need changes in these paradigms, saying, okay, you're only actually compensated if you move somewhere else. That would be the first start, right? Yeah. Also putting a minimum on and saying, okay, probably 10 years from now we're projecting that your house will no longer be insured. So what is your plan for getting moved or whatever?
The whole climate discussion makes me also crazy, because I've read a little bit about these tipping points in the future. Yeah, and if we plan infrastructure measures for the next 60 years, for instance, and the tipping points will come in 30 or 40 years already, and the system, the hydrological system, could be totally different also in Denmark. Yeah. Which solution do you offer? Is there a universal solution for all robust? What is a real robust solution considering this uncertainty?
I don't know.
Sorry.
But you see some very big investments. So people are talking about a tunnel under Copenhagen that will save all the traffic issues in Copenhagen. When we looked at those plans, I think it was 4 years ago, they did not encounter or expect sea level rise into their planning scenario. I think I would do that in order to ensure that it's actually a tunnel for cars and not for water.
Yeah. Okay. So we should plan for a wetter future and for a sea level rise future, and perhaps, but I don't know. Perhaps the tipping points would say we get a colder future, more snow, less rain. But so I read this paper recently, and I was really shocked and said, okay, we are also planning for this kind of. Are there any robust solution that, or perhaps the adaptation would be better? Perhaps we should only plan for the next 10 years and not for the next 60 years. Is that so? Flexible solutions. What's about?
Yeah, I mean, when we started talking about climate change adaptation, we talked a lot about no regret and low regret solutions.
Yes.
I think we have learned that it's easier to talk about than it is actually to define it and implement it in practice. So that, yes, but there are costs, right? So if you go into the Copenhagen Metro, then at 6 locations, I think it is now, you have to walk up some stairs in order to go down to the metro. Now that's the cost of saying, okay, we don't want the water in a big flash flood, we don't want it to run into the metro. But of course there's a cost in people walking up before they walk down. That's an acceptable cost, I would say, but it does not help. And for all of the solutions, when we make, if the road must be longer, or there are some disadvantages of taking future changes into account. So that if there's no regret, then it's also a no climate change adaptation option, because then it's another anecdote. So we had back in 2007, Copenhagen, the national authorities issued their first climate change adaptation plan. And they said we're very happy. So the first thing we did was that we actually did climate change adaptation to our new national playhouse. And everybody was very happy. And I called up the guy in charge, and he's sitting here today. And I said, so what does that mean, that the government is going to be more or less concerned about the neighbors of the playhouse? And it took half an hour, and then all of a sudden that part of the press release was removed. So what is no regret and what is a low regret option, right? So what you do does, no matter what, it has an influence on what you do. So we have to take it into account. We have to make robust solutions. And that means that you can always be attacked for it not being optimal.
Yes, so the politicians has to take the responsibility to discuss always. Okay, but perhaps at the last two technical questions, perhaps perhaps you can help me here. We have some trouble if we go for hydrodynamics modeling 2D. You did a lot of that. We have big troubles to define the right roughness for this small water depths. Do you have an advice for me?
I think I can have a partial answer if we are in the cities, but you are mostly outside of the cities, I know, so no.
Yeah, but also grassland and...
I think in the urban setting, it's quite clear that the mass balance error is of larger importance than the roughness. So it's about getting the right volume. So how much water does come from the green areas? The first study we did was in Greve in 2002, where we saw that there were 30% more water than we had anticipated in the roughly speaking. Now that 30% more water came from the green areas, and no roughness coefficient changes can of course not can compensate for that, right? So in the urban area, I would say the roughness does not matter as much as the other thing.
And for the runoff generation, then, have you an advice for me? 30% is a lot.
Yeah. Are you asking about that too?
Yes.
My goodness. That's not easy to answer. I think we did some studies assuming that we had some very simple loss models of infiltration models. And there we, at least on point scale, said that we could, if we took into account antecedent conditions and what type of soil it was, we could reduce the uncertainty down from something that was in the order of magnitude of 10 millimeters down to 4 millimeters of runoff. We never continued that work onto to actually saying what's that going to mean for the mass balance. It's something that is lying on the desk, and it will appear in an application at one point.
And I think, especially in urban areas, we could install cheap measuring devices. Soil moisture is now very cheap to measure, for $10 more or less for one sensor, and you have these parks, and you can transmit it here very easily. Then you have a recording of the soil moisture. If you know the saturation, that would help a lot.
Yeah, but you still run. I mean, I fully agree, and we have people that are looking into that currently at the department. We also have to bear in mind that that is exactly one of the applications that are data-rich but information-poor systems, in the sense that you're looking at a green system that will produce a tangible number approximately once a year. Now, if you, and that one time per year always happens during vacation or regular maintenance of the equipment or some other kind of thing, so you're going to lose half of that, half of those measurements. So it's extremely difficult to actually get it running. And I see practitioners smiling because they are out there, they know what. It's extremely difficult. I mean, we would really like to go there. We would like to understand it. Yeah. Understanding runoff from green areas is a huge task, and we need to solve that in an urban setting because it's also different from the catchment, natural catchment setting. Yes. But it's not something where we do not have a well-defined strategy for doing the research, nor do we know exactly what the processes are going to be the most important.
Perhaps we can apply for a research project with the EU and getting some money for this equipment. I think that's very, very good. Okay, the last question, I'm on thin ice here, is Bayesian statistics. You showed something with the Bayesian statistics. What, in your opinion, are the pitfalls of using Bayesian statistics in the way you used it?
I don't think we did it in the wrong way.
Okay, no, pitfalls is other. You could do it wrong. Or what is the uncertainty in Bayesian statistics? It sounds so fine that you get the posterior and then you have improved the model. But is there also, let's say, a disadvantage or?
I'm just going to show. I mean, it was one of the things. I mean, Rasmus was my statistics teacher, so he would love to have see me go through this. I love Bayesian statistics in its outset because it says that your number is not a probability density function, but it's a belief that varies between 0 and 1.
Mm-hmm.
And I like that very much. So I'm not scientific in the sense of probabilities, and that way I'm much more into saying, okay, it's probably somewhere between 20 and 30%, sure.
It's like
what I hate about statisticians that are using Bayesian statistics is that the true believers always say, okay, we should go in and use non-informative priors, and then we go through the entire thing, and then you end up with a result that actually is exactly the same as you would have done if you'd done the frequencies approach. So I would like to see some Bayesian statistics that are actually using the Bayesian method of also having some prior beliefs, putting that into the system, and that have some weight.
Mm-hmm.
So that's my complete non-Bayesian, non-statistical engineering sense of it, saying that if you want to say that beliefs matter, then you should also put that belief into your model, rather than saying, oh, but I don't want to force the model anywhere, so therefore I will take the assumptions that ensure that I could as well use a regular approach.
And the prior belief is strong, so I don't know. Because it's really biased by the prior, of course. Mm-hmm.
Yeah, but...
is it, so I don't know where it was in which paper, but so that is my question. Is the belief in the prior good enough that we can use it? So.
I'll put it the other way around, saying just as a one of the parameters theta here. That is the, it's a model that we estimate that very completely freely in the model, so it could have any value between 0 and infinity.
Mm-hmm.
If it has a value that's let me see now, -1. So if it has a value that's larger than 1, then it means that we know less about the future than we know about the present.
Mm-hmm.
Still, we apply a non-informative prior, but I say, okay, of course we know intuitively that we know less about the future than we know about the present. So I would say that having theta here restricted to being larger than 1 would be a prior that would make sense to me.
Mm-hmm.
Because I mean, we did the estimation with a non-informative prior, and theta turned out to be larger than 1, so everybody was happy, right? But if we had gotten a result saying that we know more about the future than we know about the present, then I would be somewhat concerned. So
okay. Uh-huh. Yeah. Okay.
So as an example of
yeah.
my understanding of Bayesian statistics, apart from that, Maria was the one who did the analysis, and it was really fun, and she was very much into Bayesian statistics. But we had this discussion, and the paper is completely weird because we had a reviewer who was completely mental and demanded that we actually did both the full Bayesian approach and the full frequencies approach. So the paper basically contains 2 papers that are full and should be being separated into 2. But that's what happens sometimes.
So that is for me an incentive to dive a little bit deeper in Bayesian statistics.
I just add that I didn't have to make these conditional probabilities. I'd still be working on it, I think.
Mm-hmm. Okay, I think I needed 45 minutes. It's enough, or do I have to finish another 15 minutes? Yes, thank you very much, Karsten, and now.
So thank you very much, Professor Disse, and that concludes the official opposition of this thesis defense. I have one unofficial opponent ex auditorio, and I'd like to pass the microphone to Dr. Technicus Steffen Foss Hansen.
Yeah, I had to hear you say that, Rasmus, so that's the reason why I'm standing here. No, just kidding. Karsten, first of all, I want to congratulate you on the nice work that you've done. We've shared this journey a little bit the last couple of years, and it's a great pleasure for me to be here and see you achieve the pinnacle of your career, as the way I see it. It doesn't have to stop here. The history of the ring will tell you and let you know that there's actually a few Danes that have more than just one ring. So maybe that's motivation for you in the future. There's a few not so funny questions that I thought I might pick up on, because I can't sit here for so many hours and not have questions. But one thing you said is the thing about vulnerability. You seem to be calling on the one hand for somebody to define an acceptable level of flooding or flooding frequency. And on the other hand, all the recommendations you have and all the anecdotes you have actually tells us that you don't need to have this set in stone. And the reason, like you've also indicated or referred a little bit to chemicals. And in Europe, we don't have an acceptable level of risk when it comes to chemical risks. But in the US, they actually do. And those were set by the courts. It's 1 in 1,000 when it's occupational. It's 1 in 1,000,000 when it's environmental risks. And it doesn't seem that the Americans are doing much better in protecting their public or the environment when it comes to chemicals. So are you really sure that you want somebody to define this? And if you do, who? And where does it fit into slide 40 on up there? Because that I didn't quite, yes.
My goodness. You have 2 good eyes, Stefan. Oh, shit. I guess you're right that I don't need somebody to define the standards, but I need somebody to say, if we have in my understanding, you can have it both ways. We have a very flat optimum. So if we build larger infrastructure, we have less flood costs, and vice versa. If we increase and continue to have high awareness on people on flood risk, then they will have less. Then they will know what to do in case of an emergency, and therefore they will react the right way. All of these things count towards us building a more safe society, because that will keep people happy. But we will have to find a way, this is my personal belief now, saying that we will have to enable structures that ensure that we are building these structures that enable people to be protected. I mean, building a sewer system is the most cost-effective thing that any society can do. Building a safe water provision system is the second most efficient thing that a society can build. Still, 1/3 of the population in the world have no safe sanitation, and it's I think it's 1/6 is also needing pure water. That's because the people taking the decisions are deciding on behalf of somebody else rather than themselves, right? So the Asian Development Bank is having a huge problem getting the capital costs to ensure that people are getting a better life in countries where there's too little cohesion between the people making the decisions and the people suffering from those poor decisions. I'm making a call here in this thesis to try to ensure that we get better protection standards for the benefit of all, but it will ensure that the utility companies, that there are schemes set up that doesn't require the utility companies to be negligible towards the fact that when they save money, some people are suffering.
But like, if you have a couple of animations
Stefan
on
is
that
more
slide.
of a science politician.
I'm just wondering, like, for instance, the IPCC 2040 diagram.
Yeah,
it's been a few years since that. Like, is that working well? Is that how we make decisions now? Because it sure looks like it, I think.
I mean, the IPCC has taken a system that works within several of the domains that we're working in, technical domains. So it works within industrial plants, so chemical production. It works within the aviation industry. It works also to a large extent within railroads, so transportation as a whole. And I think the IPCC should be recommended for trying to say we should have something similar working also on more complex systems. I think that's another way of framing what Haley was also saying. The fact that IPCC has not succeeded in making this work on a sufficient level yet does not mean that it's not good. It means that there's more to do.
Yes, okay. So the final point, is related to the last two slides you have. The one on social engagement and the one on drivers for change. Because I'd really like to know what you were planning to say on those two slides. It's 72 and 73.
Oh my goodness. Stefan, you have two good eyes. Those are the ones that were spare ones. If it was actually it was two drivers that were part of my conclusion that I had to cut out because I didn't have time. So one of them was the thing that Markus Diesel was talking about, aligning urban and rural hydrology. So that was the one slide, and I think Markus and I already talked about it. So this is a visual representation of the same catchment. Here we have Trolle from Aarhus University. Oh, sorry, this one. Okay. That was actually also a political statement from my side. When I came out here 12 years ago, what really annoyed me was the fact that we were at the universities much poorer at working in a transdisciplinary way than many practitioners. In practice, you need to make things work, and you spend a long time on doing that. Since then, I've seen many governance structures in society change so that we actually are finding it more hard to work in practice on transdisciplinary items, finding transdisciplinary solutions, so that although actors see that this is actually a better solution, they cannot implement it because they are restricted by some governance structures. Whereas I see here, and it's of course to brag that we have that paper coming out soon in the Royal Society series in the UK, saying that we are seeing that the scientists are getting better at working in a transdisciplinary way. So that here we have Roland and me doing the flood risk, geographers, some economists doing some tipping point analyses, architects, etc., people making narratives. So I see this shift as the research realizing more and more that we need to work in a transdisciplinary way in order to find good solutions, while in real life, where you should be implementing the multidisciplinary solutions, it's getting harder and harder because of restrictions. And I see that as a huge issue, and I have absolutely no way of saying how it should be solved. But I see it as a problem in society. I hope that was...
Thank you very much, Stefan. And that means that we are now close to the formal ending of this session. I'd like to again thank the opponents, the official ones, the unofficial ones, the audience, and of course the doctoral candidate. Immediately after we leave the room, the assessment committee will convene and make their decision on whether or not to recommend to the academic council that the degree Dr. Technicus should be conferred upon Karsten Arnbjerg-Nielsen, and then the academic council will take that decision in their meeting on February 17th. And if it's a positive decision, then the president will present you with a doctoral letter at the annual commemoration party on April 24th. So we, of course, we cannot congratulate you on the degree right now. So what we can congratulate you on is that your part of the work is now finished. Answering the questions, giving the lecture, preparing the lecture, writing the thesis, and doing the research in it. Congratulations on coming so far in this process. This session is now formally ended, and I invite everybody to join us for a drink in the lobby just outside.
Yeah, really.